Let's talk about another particular kind of noise that also has a lot of application in time series. It's something called white noise. It's one particular kind of random process. It's extremely important. It's defined by the fact that it is stationary, weakly stationary, and any two different values have no covariance. Now, what is covariance? The covariance of two variables is the expected value of the product of their deviations from their respective means. Here's the equation. The covariance of x and y is the expected value of x minus its expected value times y minus its expected value. A little algebra enables us to determine that another equation is that the covariance of x and y is the expected value of x times y minus the expected value of x times the expected value of y. So the covariance of two quantities is the difference between the expected value of their product and the product of their expected values. In a way, this might make you think that these two values are independent, but that's not necessarily the case. It just means that they do not have any covariance. Now, since white noise is stationary, its expected value doesn't depend on time. The expected value of x sub n has to be the same for all times. So it's some constant, we could call it mu, where mu does not depend on time. So it doesn't depend on the time index. The second moment of the distribution for xn also has to be constant through time because it's stationary. So the expected value of xn squared also has to be constant, and that's equal to mu squared plus some other constant, I'll call it sigma squared, which defines sigma squared, the variance of the time series value. So for white noise, it has a constant mean value, which is often written as mu, and a constant variance, which is often written as sigma squared, and the expected value of a data point squared is mean squared plus variance. Now, the variance itself is, of course, just the covariance of a value with itself. The variance is the expected value of data times data minus the expected value of data times expected value of data. So it's just the covariance between any given particular value and itself. Now, there's another part of white noise, and that is the covariance between different values is zero. There is no covariance. That means that the expected value of xj, xk minus the expected value of xj times the expected value of xk has to equal 0 for j not equal to k. That is to say, for two different values in the time series. This means that we can say in general that for white noise, the expected value of the product of two values, xj times xk, is equal to mu squared plus sigma squared times the discrete Dirac delta function of j minus k. If j and k are different values, that discrete delta function will be 0, and the expected value of the two variables will be just their means squared. If j is equal to k, the Dirac delta discrete function will be 1, and the expected value of the product will be mu squared plus sigma squared. Now, a time series which obeys these requirements, that the expected value of a single variable is a constant mu, and the expected value of a product of two variables is the same throughout all time given by this equation, that is a process which obeys what we call a white noise process. By the way, there's another kind that's kind of interesting and important. It's called IID noise, or independently identically distributed. Now, for this kind of noise, different values aren't just not covariate, they're actually independent of each other. Now, that means that the joint probability density function for multiple values is just the product of the one variable probability density function for the different values. The probability of x1, x2, x3, etc. is the probability of x1 times the probability of x2 times the probability of x3, etc. And furthermore, since this kind of noise is identically distributed, all those probability functions are the same function. Now, it's not too hard to see that for IID noise, all the joint probability distributions are time translation invariant. Therefore, IID noise isn't just stationary, it's strongly stationary. One particular kind that's very often used when doing analysis, sometimes it's used even when it's not necessary to use that, is something called Gaussian noise. That's not just independent and identically distributed. We hypothesize that the probability density function itself is the normal distribution, also known as the Gaussian distribution. And that's given by this equation right here. That is the probability density function for the normal distribution. And it often happens that when we're considering IID Gaussian noise, we assume that the mean value of the noise is 0, which gives us what may be the most common kind of specific noise assumption, and that is 0 mean Gaussian independently identically distributed noise. That means that each individual value follows this probability density function, and different values are independent of each other. They have no dependence on each other, nor do they have any effect on each other. I'd like to talk about something called correlation. We looked at covariance of two quantities, and it's the difference between the expected value of their product and the product of their expected values. Well, correlation is very similar. It's their covariance which has been scaled by the square root of their variances, that is to say, by their standard deviations. Now, therefore, the variance is the covariance of a variable with itself, so the correlation of two variables is the covariance of x and y divided by the square root of the covariance of x with itself times the covariance of y with itself. In case you're wondering, why do we do this? The reason is that it removes scale from consideration. Suppose we have two variables x and y, and we rescale those quantities by multiplying them by constants alpha and beta and define new quantities. X tilde is alpha times x, y tilde is beta times y. Then the correlation of the rescaled quantities is not changed. It's the same as that of the original quantities. Now, it's easy to see that the correlation of a quantity with itself is exactly equal to 1. The correlation of any two quantities is always between -1 and +1. When the correlation is +1, we say the correlation is perfect. They are perfectly correlated. In fact, that means they have to be identical. When the correlation is -1, they are perfectly anti-correlated. In general, unless we're taking the correlation of some random variable with itself, the correlation won't be either one of those extremes. It'll be somewhere between -1 and +1.